purpose of this video is actually to do the understanding for how to read this graph and how to use this graph, and what are the things that you need to sub in order when you are calculating certain things. Okay, so also one very important thing is that if you remember, my equation, my force vibration diagram itself has a flaw, has a very big flaw, which totally does is very tough to be used to explain this scenario. This is why I say that I just want to go through how to use this thing, that's all. I'm not going to give you the meaning, okay? Because previously we said that if you were to pull this mass down, okay, it will start to oscillate, okay, and then if you were to have a damper, you actually have a lesser oscillation, okay, which in fact is wrong, okay. Everything is dependent on the forcing function itself, okay. So if you have an oscillation like this, everything is due to the forcing function. However, if the forcing function is lesser, you oscillate lesser, and if it's lesser and lesser and lesser, you oscillate around the static area. Or perhaps I may be wrong still, okay. If the natural frequency of the forces acting on it is same as the natural frequency of the system itself, then you oscillate around the so-called the x naught itself, okay, with the when x doesn't move, okay, around, you oscillate around the static position. If the so this one is the frequency of the forcing function, I would say, is equals to the natural frequency of the if the frequency of the forcing function is equals to the natural frequency of the system, you have a very large resonance, okay. You resonate and then eventually you will break off, okay, because this portion over here and this portion over here they will actually can't take hold of the resonance. This is why we invent a damper to actually damp out. The damper itself is actually, let's say if you oscillate like that, right, if you pull it down and you return, the damper will let it return smoothly instead of very fast and whatsoever. So damper itself is actually to damp out all form of vibrations, that's all. And if it goes in detail wise, I can't explain it anyway. So it's a very complicated issue, which I find it totally tough. And nonetheless, let us start off with this thing. As I say earlier, if still I may be wrong. So if the frequency of the forcing function is equals to the frequency of the natural frequency of the system, the natural frequency of the system is just the spring itself. Okay, how the system would react with just a spring itself, that's all. Okay, without any forcing function and without any damper. So it's just like a free damp thing, so we just oscillate. So this one simply is just a natural frequency. Okay, so this relationship is actually beta, what we calculated so far along our way. So this is the frequency rate. So as I say, if this is equal to this, then this means that this equals to 1. So the ratio between them, if it's 1, will be a resonance, okay, as you know, because if you were to bring this up, you will be, so therefore it's very dangerous if you do that. So if you are given any questions, they will give you may also need to calculate your frequency of your forcing function, or they are given to you, and the natural frequency in order to verify the beta. And if you get the beta ratio as equals to 1, you have a resonance. Okay, resonance, this one, if I'm not wrong, okay, this y-axis is the amount of resonance. It measures the amount of resonance. So the higher you are the resonance, the more the resonance is. As you can see, the frequency ratio, the beta, as you reach 1, okay, the resonance itself is the max. It goes to infinity. So if you reach this stage, yeah, your system is gone. Okay. So therefore, and nonetheless, this xk over here, this x, okay, is, I don't know whether this x, does it belongs to the same x that we derived this x over here. Okay, I don't know whether is it this x, because if you bring this f naught down, this is the forcing function. I mean forcing equation. You get this, right? So I don't know whether it is. So this is the portion. There are also another below. So I don't know whether this x, what is this x actually meaning is. Is this x the same as the x that we are looking at here, or what is it about? But nonetheless, the meaning itself is the resonance, it says. So typically you'll be given these values also. So when you're using this graph, make sure you know what we are talking. So so in order to prevent any resonance, we actually add in damping factor. I mean damper. So when the damping factor, so when there is no damper equals infinity. If there is slightly small damper, you will have a slightly more controllable curve, but it's still much of a high resonance. And then as the damper goes, as the damping factor increases, as you can see 0.25 already, your resonance start to goes down, and then it start to go down, and eventually when you reach 1, is critically damped, you just go down here again. So it is pretty much the case. And then in this example, in this plot, okay, this plot is still using frequency ratio as the x-axis, while now we change the phase angle. The phase angle in this case is what we have just derived, the phi, angle phi. And my explanation for this one, the amplitude of the damper and the and the relationship between kx and acceleration is also wrong. Okay, please. So this is also one issue that I'm talking about. Although the relationship is there, but then there is some blur area that I can't understand. So I have to make clear. So this is exponential. So if it's damping factor equals to 1, your curve is like that. Okay, so when your phase angle is 90 degrees, okay, and when your phase angle is 90 degrees, and this is the frequency ratio is 1, and this point is where your system goes to infinity, right? So if your phase angle is equals to 90 degrees, which means that your whatever, that means your, how do I say? Okay, hold on. Okay, that means your damping factor is equals to the forcing function. Okay, if it's 90 degrees, because eventually if the angle is smaller and smaller and smaller and smaller, I mean if this end is bigger and bigger, okay, let's say at first it's like that, right? So the angle is big. So if this length is getting longer, the angle is bigger. Eventually when it reaches just this point, the angle is very big. It's nearly to 90 degrees, right? So you're saying that the damping factor, the damping coefficient of the system is near to the frequency, the forcing function. So this relationship tells you that the phase angle, it relates you to the forcing function and the damping coefficient, and there's totally no meaning. I don't know, I can't see the meaning in there. So therefore, I say that my previous explanation is totally cannot make it. So the only thing you need to know is that when you see frequency ratio is 1, that's it. Your system goes to infinity. You cannot do anything. Okay. And then if your damping factor is lesser, you have this angle. Your angle, in this case, your angle will rise very fast. Will change very fast. Okay, I don't know what it means. Maybe your phase angle will actually increase so-called much faster than the higher damping factor. So the lower damping factor, as your frequency ratio increase, you have a higher angle, phase angle, then you will have a higher lag behind. Okay, so lag behind where they are. Especially I said that this is the forcing function and this is the displacement, right? The phase angle is the lag behind. It's now I think it's partially correct. Okay, there's some things I also want to understand. And while I say that the unknown forces is damping forces that prevents the displacement from displacing the correct thing is wrong, absurd, rubbish. So don't care about this thing. And then yeah. So the meaning simply is just saying that if you were to have the damping factor, you will decrease the amount of resonance. Okay, you will decrease the amount of resonance. The y-axis is the resonance. Okay, the x-axis is the frequency ratio. Okay, so let's say if your natural frequency is equals to your system system frequency, if it's 1, but however if you have a damper, the system will not fail. So this is why a damper is very important. So with this said, I think I've made things clear, and I have a lot of stuff. So I'll just put comments in the previous videos so that you will not be confused. So in the next video, I'll just do a summarization for the whole lesson 4, and we call it a day. You see, I start off from morning 9, I do until now, I haven't finished yet. So I'll see you in the next video.